Hello. Earlier, I explained probability is like length. That is not wrong, but the main reason why I explained that way is to explain the concept that one point has no length. So one outcome has no probability. So that's the only reason why I explained probability is like a length. But it was not general enough. That comparison was kind of useful to give you the idea, but not general enough to make to be applied to all possible cases. So as I said, I'm going to use area now. I will use area. Then how can we generalize it? Here it is. It becomes a little more complicated. So this dimension is what you have. Like say this dimension, horizontal dimension is the amount of coffee. Coffee amount is on here. So it's supposed to be 12, but can be smaller, can be more than that. And on the vertical dimension, there is another one. This is the additional dimension. And what we are doing here is we draw a graph. A strange graph, like a step graph, like a lot of boxes, some kind of strange graph. And I am going to, from now on, I'm going to, so previously we considered probability is on interval, length of an interval like this. So between 11.9 and 12, the length is here, but now we are going to extend it to area up to this point. So probability between 11.9 and 12 will be not the length, but the length times height. Height is given by the graph from this point up to the graph. That is the area which will give us the probability. Like this. Exactly. So probability in between 11.9 and 12 can be calculated this way. First, the width is obviously 0.1. Difference between 12 and 11.9. The width is 0.1, and you multiply the height. Height is 2.5 because this graph, the graph is at 2.5 line, right, on the vertical axis. On the vertical axis, this point is 2.5, so you multiply 2.5. That gives you 25%, which is consistent with our example. The number that I gave you earlier. And similarly, now think about this. You can calculate any area in this simple graph. So think about probability between 12 and 12.1. The length is also 0.1, right? Length of the interval is also 0.1, but now the height is higher. Height is taller, so this graph is higher than this point. So the higher point is 3 on the vertical axis. So 3 is the height and the width is 0.1. So as a result, 30% is the area. The area is exactly the probability. This is general. So this way, by depending on how you draw the graph, you can change the probability. If the graph is higher, then there is more probability on the same interval. And so, as you compare, same interval, but 30%, and here 25%. Additional dimension is added. Same interval may have different probabilities. And it doesn't matter even if the shape is not a rectangle. So if you're interested in probability between 11.9 and 12.1, then you need to calculate this area below the graph on the interval. This area. To calculate this area, you can divide them into two rectangles and calculate area for each rectangle. That's what you learned in elementary school, right? I expect my son can do this maybe in 3 years, 2 years. He's now in kindergarten. So anyhow, it's easy. Like calculating the area is what you learned in elementary school. So I would not explain how to calculate the area. So, but instead, we will go more abstract. So that kind of graph, this graph is important. That's what determines the area, and so the graph is what determines the probability distribution. That graph is called probability density function. Probability density function, which is usually denoted as lowercase f. Remember, the CDF, the cumulative distribution function, was denoted as a capital letter F, but now PDF, probability density function, is denoted as lowercase f. And given the PDF, you can define the area under the curve, under the function on a given interval. That is the probability, right? For any continuous random variable, there exists such a density function. So, and of course, it should be always non-negative, but it may exceed 1. It is always non-negative because the area cannot be negative. So it is always above the horizontal axis, but it can go beyond 1. Even if the probability is probability must be smaller than 100%, but the density can go beyond 1 because you are going to multiply this to the length. So, so this means 300%. 3 is 300%, but it's not a probability. So 3 is not a probability. It's something that gives you a probability when you calculate the area, but itself is not a probability. More rigorously speaking, it is a density, right? It's like the mass and the density are different. Like that, this is the density of a probability. Mass is probability, but this number is like density. So probability density is how we call this guy, this value. Here are some examples of PDFs, probability density functions of some well-known distributions. For example, uniform distribution has a flat flat density. So 0 here. When the density is 0, there is no probability. And probability is put on here on this interval, and it is uniform. Equal probability on the interval between 1 and 4. And exponential distribution has the most probability near 0. And that probability becomes lower and lower as it increases. Right? So probability becomes lower. And this is a gamma distribution PDF. Gamma distribution has most peak at 1. So most probability is put on 1, and then it goes down, right? Gamma distribution. And normal distribution is the bell curve, the curve that you know. Bell curve is for the normal distribution. So far, I spent this lecture to give you the idea of continuous random variables, and we get the normal distribution at the end of this lecture. You do not need to know what these guys are, but I just wanted to give you there are many different shapes of probability density. And the area between 1 and 2 can be calculated this way. So probability between 1 and 2 in the uniform distribution is like this, exponential like this, gamma like this, normal like this. So the idea is the same. calculation will be a little bit more complicated, like because it's not a rectangle. You don't need to do that. Computer will do it for you, so don't worry. And to take another step, one step further, I want you to understand the area as an integral, right? So the orange area is the area below the function between 1 and 2. This is exactly what we calculate with the integration. So integral from 1 to 2 of fx dx is this area, right? So the orange area is the result of this integral. So probability it can be understood as an integration. I'm not going to use integration again at all, but I want you to give you the connection between probability and integration. Later, if you go to a more advanced statistics or econometrics courses, then this concept will be important. You need to know calculus, and you will utilize the integration properties of integration to better understand the probability and probability density, right? And so far, let me summarize. So, like first, I told you the important points are we are considering continuous random variable, and continuous random variables have different characteristics from the examples we considered so far, because it has uncountably many possible outcomes. So we cannot list all the possible outcomes, and one outcome has no probability. They make a huge difference in our approach, and as a result, we have to use a different approach. And there are two possible alternative approaches. One is using the CDF, cumulative distribution function, and I showed you simply I demonstrated how we can convert the cumulative distribution into different forms of probabilities. Also, you may use the probability density, which is an area. Literally, you can calculate the area for any interval, right? Using the integration. The point is integration, and if it is rectangle, it's simple area. But if it's more complicated function, you have to use integration. It's not a big problem because computer is going to do that for you. So don't worry too much about integration. That's all you need. I will not use integration again. And so this is it. This is the end of this lecture. And next week, next lecture, I'm going to start normal distribution. I will introduce you the normal distribution, the most important distribution in any science. So that's why the name is normal. Any other distribution is abnormal, right? How arrogant it is, the name is, but it deserves the importance deserves guarantees this name. Okay, thank you for watching, and see you later.